All right, let's go over this. Oh, come on. All right, so I'm just going to talk a little bit about today some security stuff. It's kind of not related to FPGAs at all, but I don't know. This is the research I'm doing, so I can actually talk very well about it. So essentially what we're going to go over today is essentially using machine learning and phase prediction, kind of trying to figure out what's going on using some machine learning techniques. Some models. Like last class, we talked about how, I went through that little example on Google Translate and how contextual information can change or improves analysis. So for side channel attacks, you don't know what side channel attacks are because you're not in the other class, but side channel attacks, and this would be a great introduction to the other class if you would like to take 466 in the future. CST 466 would be a great elective if you're CET, and it's a required class if you're embedded. So side channel attacks are essentially attacks that target an underlying implementations. You could have, like, if you had an LED light, an LED indicator, that LED indicator, your hard disk drive indicator, could be flashing the data off your hard drive. It's not, right? It's not, but there's a lot of indicators that hook directly into the data line. That's called a side channel attack. You're not attacking the system, you're just attacking some leakage of the system. So EM emanations, electromagnetic emanations can also be attacked. And what I work in is a power-based attacks. And you can essentially use these to extract information like encryption keys or instruction sequences. So you have a circuit, and this one does go back to FPGAs a little, or essentially CMOS-based systems in general. CMOS systems, they leak information inherently because you have a transistor, and these transistors leak information depending on, you have register 1, register 2, register 3. What's being stored in that register, right? You essentially, depending on what's being stored in that register, it's going to use a different amount of power. A transition between 0 to 1 is a charge, 0 to 1. A 1 to 0 transition is a discharge. A 0 to 0 or a 1 to 1 transition is no transition at all. It's really just quiescent current, steady state power consumption. So we've established here that circuits use different amount of power depending on, 1, what the instruction is that's executing on the microprocessor. 2, what is the data being stored, right? And this is true of all devices, FPGAs, CPUs, anything CMOS based. Essentially, you have 2 things called Hamming weight and Hamming distance. Hamming distance is the difference in the number of ones between two registers, or 2 values. Hamming weight is the number of ones in the signal. And if you're on a microprocessor, the instruction type, if you're doing an XOR versus a load instruction versus a store instruction, you're going to use a different amount of power, okay? FPGAs are a little trickier because you can do a lot of stuff in parallel. Once you do stuff in parallel, you kind of hide or you mitigate some of the leakage. So you can essentially do a couple techniques to get rid of this leakage. You can redesign CMOS, right? Complementary metal oxide semiconductors inherently leak information. You can design it to stop leakage. You could purposefully inject noise into the circuit or otherwise reduce the signal to noise ratio of the leakage. You could use a charge converter or a capacitor, and you can obfuscate code as well. You could prefer masking on it. You could do bit slice programming or fake instructions as well. Just insert a bunch of random garbage instructions. So there's a couple different techniques to mitigate leakage from a system. There's something called bit slice programming, and you're used to doing things like XORing stuff together, right? You're used to doing things like XOR one register to another register, okay? But in this bit slice model, what they're doing is, instead of arranging it register by register, the data is stored vertically instead of horizontally. You just end up executing the same, you end up executing the same set of instructions, maybe more instructions, but you store the data vertically instead of horizontally, okay, to hide the leakage. And this one should be simple, you should be able to decipher what this is. This is an example of a feedback loop where, you know, if you always consume the same amount of power, it's going to be hard for an attacker to figure out what your processor is doing. So this is just that amplifier, transimpedance amplifier. This actually is very similar to the, it's not that similar, but you're essentially sensing some information, feeding it back, essentially charge pump. So increase or decrease the charge to increase or decrease essentially the current source here. This is very similar to how the PLL works in the class, right? We had that feedback loop, that negative feedback loop essentially controlled a charge pump in that scenario. That charge pump would control the voltage controlled oscillator. In this case, it's just controlling how much current we sink into this. Okay. Here we have a redesign of circuits. So instead of using CMOS directly, they implement a pre-charge and evaluation phase, and they operate everything in parallel. The opposite value, you get the opposite value out. You always do everything in parallel to reduce or mitigate the leakage. And here's another technique to essentially decouple the power supply from the circuit. So there's something called simple power analysis. Simple power analysis is essentially saying, we look at the scope trace. And you know, normally in this class, we'd go look at a lot of scope traces, but guess what? We have no scopes this term. So this is the best we're gonna get. Look at these traces. This is a for loop password checker, and the password is hello. Can everyone make out on the screen, like there's like this kind of like unique position that you can identify in the trace, like right here. Can everyone see that? Yes, no?
Kinda, yeah.
Yeah, there's a, and then you move along and you'll see this position change depending on how many correct characters there are. The password checker is essentially checking character at a time and breaking out of that loop. So if it gets 1 correct, it's going to break out earlier than 2 versus 3 versus 4. This is a side channel attack, right? We're targeting the power leakage, but it's also an example of a timing-based attack, right? If you're working on some sort of software implementation and you're trying to check whether something is true or not, and you call this function and you say, check whether this is true or this is false. Maybe if it's not a constant time function, the function itself will take 10 seconds versus 5 seconds. Okay, it doesn't take 5 seconds, but it's not going to take that long. But a correct response would yield 5 seconds versus a wrong response would yield 10 seconds, or vice versa. If you can kind of time the difference between those two functions, then you can determine what's going on. That's another form of side channel. Side channel is not just hardware. So,
Kevin?
What?
On the previous slide, so you were talking about the pattern. Is the pattern that like one little spike in between all the other ones, where it's just like a single up spike?
Yeah, it's kind of like this. I'm looking at this one. This is really easy to see. This like white spike right here. That's a spike I'm talking about.
Okay.
Okay. So if we're running an algorithm on our CPU, we can actually determine what's running on the target device by just looking at the power signature. Okay. This is kind of useful, but it's also not useful. But what we can do is essentially apply some statistical analysis in the form of correlation power analysis. We perform some statistical analysis. This is actually an encryption algorithm. We went over encryption earlier in the form of your test bench. So we can attack the implementation and actually use a correlation coefficient amongst many traces of this and extract the encryption key. And we get this correlation coefficient that tells us the encryption key. Remember, AES 128 had 16 bytes, so it has to attack 1 byte at a time. And this is going back to something, this is actually relevant to our class, which is the sampling rate of a signal. If we synchronously sample something, we're going to be better off with respect to sampling rate. And this was back that day where we were talking about sampling rates and aliasing. We don't have to worry about aliasing or anything like that if we have synchronous sampling. That is, the target clock and the scope clock is the same clock. Unfortunately, that's not usually the case. Now here's a slide that shows you, here's a sequence of instructions, okay? Here's a sequence of instructions. There's a single move, these are no ops, and there's a single move. We look at the variation here. The variation here and here is going to be the variation in data. This is the data variation. This, the difference between the green and the red, both of these right here are move instructions. But both of them, the shape changes depending on the instructions coming before the current instruction of interest, okay? You see the mean, max, and standard deviation here. This is the instruction versus the data. And here's an example of four different sequences of instructions. You can see that the move instruction completely looks different depending on, essentially, it looks completely different depending on what comes before it, right? There's an effect on the instructions that come before it. If we relate this back to that example of the Google Translate, you can see here, you can still use the same type of concept here with Google Translate when we're doing the example of contextual-based information. You know, that those words have, in a certain position or order, have a different meaning or have a different probability. Yeah, I'll skip that one. So, did we go over hidden Markov model yet?
I don't remember.
I don't think so.
No, we haven't.
We'll hit on this later. This one's not important. All right, so let's get back to the machine learning side. So when I capture data from the setup, I'm taking data from an oscilloscope from the victim device, that microcontroller, set up as follows, to a host computer. Now, in my 466 class, you learn how to automate a scope. Hopefully we go back to normal and we'll actually use a scope normally. You have to capture thousands of traces at a time sometimes. So you have to use automation. Python's great at automating the scope for you. So the process is as follows. How do you attack a system, right? You collect the data. You just start collecting the data using Python and a scope. You have to classify the data, right? You have to classify, in this case, what is this research classifying? It's classifying different types of instructions from the power signature. So if I guess I forgot to mention that part. If we try to classify an AND instruction versus an XOR instruction versus a load instruction versus another instruction on the microcontroller, we're going to get a different, we should be able to classify, right? We talked about classifiers last class, so we're actually using a classifier in this case now. And we talked about LDA, naive Gaussian Bayes, and k-nearest neighbor, right? Linear discriminant analysis, we talked about a little bit. Naive Gaussian Bayes, which was a normal distribution, that P probability of A given B equals something. And then the KNN, where we had essentially saying, I'm going to be associated with the nearest neighbors, right? The X number of nearest neighbors near me, I'm probably the same class. You can think of that in terms of neighborhood, of people where people live too, with income levels, right? People clustering near the same income level. And then you do dimension reduction. We talked about dimension reduction last time. Dimension reduction was the idea of, if you have too many dimensions of data, then maybe each dimension, some dimensions are worth more than others. Or maybe having more dimensions of data will help you classify information, right? We talked about this with the orange example, the diameter of the orange, the color of the orange, the texture of the orange. What else? The weight of the orange, right? These are all different features of an orange, or essentially dimensions. In this case, dimensions with respect to this instruction set, the dimensions of data would just be, if this represents, right, from here, this point to this point represents one instruction, you'd have 8 points of data. That's 8 dimensions of data, right? 8 points, 8 sample points for that single instruction could represent 8 dimensions of data to correlate, or features to correlate, to identify that instruction. Okay, we talked about the idea of the curse of dimensionality, where we have too many dimensions of data, where it takes too long to process, and some of the dimensions don't even matter. So too many dimensions might also be a problem, which is why we perform dimension reduction. And the next step is to enhance the collected data. Hidden Markov model might be used in this case, as well as a forwards algorithm, right? We'll get to that in a minute. But essentially, I wonder if that's the case. Hold on. Oh yeah, we'll come back to that. So this is an example of when we collect a trace. You can clearly identify using just simple power analysis that the add round key lives here, here, and here, right? So we essentially did a trace collection, and we can identify each of these algorithms, right? Obviously, on an FPGA, this was not, these wouldn't be function calls, right? This would just be built into your hardware, which would operate in parallel, which actually makes it much more difficult, but not impossible to analyze. This goes back to the one of the questions I asked on one of your, I think it was a lab, about software versus hardware implementation, and how the hardware implementation would take fewer clock cycles. So here we can now classify the instructions. The sequence of instructions, in this example, I went through the debugger and kind of figured out the sequence of instructions. You can pull the data in the trace and align to it. Once you have this information, you can do a classification on each point in time. Which point in time is correlated with which instruction, okay? So for instruction classification, each clock cycle has to be mapped to a corresponding instruction. Instructions lasting more than one clock cycle are classified as multiple instructions. It's a synchronous sampling rate of 1 to 4x. Again, we're talking about data dimensions here. Too many dimensions of data results in the curse of dimensionality. What is overfitting? We went over overfitting yesterday. And it's like your training data set is so tuned. There's so many dimensions that it's looking for that exact fit. Like that trace has to look exactly identical before it'll classify it as that type of instruction, or that type of orange, that type of apple. Too many dimensions in some algorithms can result in poor performance, and some algorithms don't reduce the dimensions of data, okay? Like LDA and QDA do. So what are different classification algorithms that we can use? We have support vector machine, we have decision tree, we have multi-layer perceptrons, which we kind of went through with the neural network stuff. We have Gaussian naive Bayes, we have linear discriminant analysis, we have k-nearest neighbor. Now let's look at this. Decision tree is pretty obvious what it does. It's just literally a decision tree. It's just like a tree. Multi-layer perceptrons was a neural network. But let's look at how much it costs us with respect to time and space. You can see KNN, Gaussian naive Bayes. You can see here Gaussian naive Bayes is a cheap classifier. It might not be as accurate though. You can see 73% accuracy or F1 score. You can see 99% on the KNN. You can see 87% on the linear discriminant analysis. It's going to completely depend on the data that you have, the data set you have, which one works better. But these are the most basic ones. What you'll usually see is Gaussian naive Bayes is a cheaper to implement classifier with respect to time and space, but the performance isn't as good. And you can see the MLPC, that the neural network, it uses quite a lot of time, right? Here's the Gaussian naive Bayes. Probability of A given B is equal to B given A times probability A over B, probability B. The probability that we go outside, given that it's raining, is the probability of it is raining given that we go outside times the probability that we go outside divided by the probability that it's raining. And again, the Gaussian naive Bayes might be fast, but it's not as accurate of a classifier. So essentially, naive Bayes has the probability of Y is the class, okay? In this case, Y is a class. So we go back to that fruit example. You could have Y being, is it an orange? Is it an apple? Is it a pear? Is it a banana? Is it what, right? The class of data. In our example here, is it an XOR instruction? Is it a load instruction? Is it a store instruction? Whatever. Is it a move instruction? It's the class. The dimensions or features, again, could be the color of the fruit, could be the size of the fruit, it could be the weight of the fruit. In our example here with collecting the machine instructions, the XOR instructions, it could just be the 8 data points that we collected, okay? So you end up with this relationship. So probability, the feature likelihood for Gaussian naive Bayes is assumed to be a normal distribution. The normal distribution is just that normal curve, right? It looks like that bell curve. Oh, okay. This is the probability of a feature or class. X sub I, these X values, are the features, right? What's the weight? What's the size? What's the color? So probability of the feature given that it is an apple, right? So let's go to KNN now, K nearest neighbor. So what is this, right? This is me classifying a bunch of different instructions. And you can see clusters forming, and this is not K clusters, but you can see that the clusters are forming. Things that are close together is assumed to be of the same class, okay? The same Y in this example. How do you determine the distance between this? You have to do there's a lot of distance metrics that you can use. The most popular and basic one is to use the Pythagorean or Euclidean distance. You do the Pythagorean or Euclidean distance to every single other point. You pick one point out of this entire graph, then you calculate the distance to every single other point. K nearest, so 3 nearest neighbors. What are the 3 closest to me? I'm going to become that part of that class, okay? It's just Pythagorean theorem over and over. You have other distances like Manhattan, Minkowski, and Chebyshev Hamming distance as well, but we're not going to get into that. Here's an example of grabbing more data. So trigram versus single, collecting more data points versus a single data point. Collecting your neighbor's data points, as well as, or just your instruction. So this is using K nearest neighbor, okay? This data was sampled 4x, which means that the single sample has 4 dimensions of data, and the trigram 3 instruction capture has 12 dimensions of data. There's no dimension reduction data here. So plotted on these graphs, I only plotted 3 dimensions. You can't represent more than 3 dimensions here. So you can see, looks pretty similar, right? Using k-nearest neighbor. Now, the next classifier is going to be the linear discriminant analysis. With linear discriminant analysis, what you could do is reduce the dimensions of data to 2 or 3 or something. Reducing the number of dimensions in data is probably a good thing because it reduces the processing time while still keeping the data there, okay? So the left and right, we had the left and the right example here. We had a single instruction with 4 samples versus a trigram cluster is a set of 3 instructions, which means 3 times 4 is 12 instructions. The standard deviation of both graphs is the same between the clusters, but the distance between the clusters using the trigram approach is much higher. You want the clusters to be far away. Once you have clusters more far away in classification, it's harder for someone to misclassify, right? It's harder to misclassify than when they're closer together. Here's some Python code as an example of how to do the k-nearest neighbor classifier. You got to include this to plot it. sklearn is the machine learning library you can use. You have to split your data into 2 sets, the training set and the training set and the test set. You use this function call here to essentially split it. Any questions so far?
Yeah. Regarding distance, so the distance determines if you're part of a cluster or not, right? Or
Yes.
Okay, I was just confused about that a little bit.
Right. So let's go back to that. The distance, you might have a like an outlier, which means it's just not like everyone else. One of these things is not like the other. But this one has pretty good clustering. So basically, if you picked a point in this range, there's a high probability that the nearest neighbor is actually going to be of the same class. Okay. So here we do, we can swap out the classifier. Here we're using the k-neighbors classifier here, but we could also use something like linear discriminant analysis or some sort of other classifier. You're going to fit the model, and then you're going to use it to predict. Then you print out a confusion matrix. That confusion matrix is essentially saying, I think this is an apple. What's the probability that it's actually an apple? Oh, I got 83% right the time, but maybe 10% of the time, I classify it as a pear. The remaining 7%, I may classify the apple as an orange, right? That's the confusion matrix, okay? How well did my classifier work? How accurate am I? It's just essentially a 2D matrix with the classes on both the X and Y axis. Classification report. That's going to give you the classes. It's going to give the accuracy, precision, and F1 score of each class. What is F1 score? What is recall and what's precision? Okay, so supervised versus unsupervised machine learning. Supervised techniques, you have to feed information in. Unsupervised, it kind of figures it out on its own. It's not labeled. The data sets are not labeled in an unsupervised method. Supervised learning, the data sets are labeled, okay? So you got recall, which is your true positive over your true positive plus your false negative. Your precision is your true positive over your false positive plus your true positive. Your F1 score is a combination of the recall and the precision. These are the metrics you use to see how successful your classification is. And here's an output that you might see in the classification. I classified 48 instructions, 92% success rate on, let's say, instruction 40, 90% success rate on essentially F1 score on 3. But the support here, the support column is saying how many data points did I really have? So honestly, this example is pretty weak because we don't have that much support data. You want a lot of support data. This I just kind of just screenshotted this. So you can see the performance of k nearest neighbors as we plot an increase in the k nearest neighbors. When we have 100 nearest neighbors, we increase the number of neighbors and the performance goes bad because there's too many neighbors at this point. And here's another example of distance metric, Euclidean, or essentially Pythagorean distance versus Manhattan distance versus Chebyshev distance. They're all very similar, but there's different ways to run a classification on the different classification distance metrics on the KNN. Here's the LDA and QDA classifier. Linear discriminant analysis performs really poorly when you have fewer data points, but when you have more dimensions of data, essentially F1 score for a trigram, 12 dimensions of data versus 3 or 4 dimensions of data, you get a significant improvement in the performance of the classifier. In this case, increasing the dimensions of the data is a good thing. Okay. Then you can scale. This one, what I want to show in this slide is this. Your k nearest neighbor, once you increase it to, let's say, 1,000 traces or more data, you push more data through an algorithm, some of these machine learning techniques don't scale very well. Look at how long it takes KNN to work. 21 seconds versus that much time for an LDA classifier. So the scaling for KNN is very poor, okay? In this case anyway. But you also have to look at it from the perspective of the memory usage. KNN uses very little memory, whereas the LDA classifier uses 27.7 megs. So you have a time, space, and accuracy trade-off, okay? So what can we do now? We can do a sliding window. We can slide a window of 200 something instructions along and say, can we detect the sequence of instructions here? Once we detect this, we can, and sliding it along, we can detect these instructions, okay? Here is essentially, I'll skip this slide. You're not going to get much out of it anyway. You can go back and read it if you want. This slide here is trying to illustrate the importance of understanding your data. If you have a lot of data and you run it through, you use more time to process data, but it doesn't necessarily give a return on investment with respect to time. Just because you push more data through doesn't mean you're going to get a better answer. In this case, 1,875 traces gives you the solution just like 5,000 traces would have given you the solution, but it's going to use less time. You have to optimize for that for your problem. So you can cut corners further by essentially using reducing the sampling rate. And this shows bad performance here. And here's another example of where we cut corners in the right way, where we have fewer number of instructions matched, but we can still determine that we're in add round key in this spot, and this spot. This one doesn't work, right? Okay, so we're gonna go back to kind of like, how do we improve this data? How do we improve the data that we collected, right? We can already see that we can determine where the add round key occurs in this function. But if we go back, okay, what if the classification wasn't that good to begin with? We have to use contextual information to enhance a signal, okay? We talked about this, right? We talked about this last time. We talked about how, you know, how does Google Translate Siri or Alexa work? You have regional dialect, you have tone, different tones, you have regional dialect, you have a microphone setup, the signal to noise ratio may be different, contextual information, you know, 2 words could mean different things in different contexts. The same word could mean 2 different things in different contexts, right? And people just have different voices. So how do we improve this model? Right? Well, let's go back to DSD1. DSD1 has, we went through state machines. We had discrete transition probabilities on these arcs. We had discrete probability like we had x equals 1, we go to the next state. Y equals 2, go to the next state. Okay? Y equals 0, stay in the same state. These were discrete transition probabilities. Now, forget about that, or take those away, those discrete probabilities. Replace them with actual transition probabilities, right? A number between 0 and 1, the probability of transitioning between one state and another. Now this becomes a Markov chain. All the states and the transition conditions are fully observable. So we've taken our discrete implementation, let's say from DSD1, we push through the arcs, the arc transitions are now probabilities. What's the probability that this word comes after this word, or this word comes after that word, right? So we look at this from a Markov model. It turns into a Markov model now. Okay, so we can use a Markov model to enhance low quality or noisy data. So unlike the chain, not everything is fully observable. So the Markov model can be used to enhance a noisy signal using prefabricated contextual information. So given a sequence of observed instructions, what's the probability that the sequence was generated or belongs to the model in question? That is, you know, if you have a unique algorithm, running on a microcontroller, there's going to be a certain pattern of instructions depending on what it's running, right? This instruction is usually going to come before this instruction. That instruction is going to usually come before this instruction. In the English language, or when you're translating, one word spoken is usually going to be followed by these words, or this letter on your keyboard when you're doing a prediction of what the next word is going to be, or Google's trying to predict what's the next word or letter you're going to type. It's going to be a probability of going to A, to B, to C, or this word, that word, this word, or that word. Okay? Unfortunately, some of that information is kind of private and stored, and you can tell after a while you're using your keyboard, it'll predict certain words because you generally type those words. And it's using a model similar to what we're talking about here, okay? There's 3 problems that you can solve with the hidden Markov model, or you can represent a hidden Markov model, or sorry, hidden Markov model. One is a sequence of observations. What's the probability that the observations are generated by a given model? The next one is, what's the most likely state sequence in the model that produce the observations? The last one is, how can we improve our model given this information? How can we improve our accuracy? So that's Forward, Viterbi, and Baum-Welch, which we won't get into. So you got a hidden Markov model with these instructions. You have a sequence of instructions. You have to go, you have to go into Atmel Studio or whatever, and essentially go through walk through every single instruction, and you'll see the probability of the CMP instruction, the branch not equal instruction, is 7%. From the store to add instruction is 5.6%. Then you put it into a transition table. This is the AIJ matrix. The probability of add, a store followed by, an add and then a store is transitioning to a store is a 0.27%. Going from add to load is 2.65%. You map these probabilities out. Then you also have, classified this information already. So this is saying instruction 12 is successfully classified 86% of the time. So if I think something's an instruction 12, right? If I think this is a store instruction, I'm right 86% of the time. So given those 2 pieces of information, you can construct a model. I don't know if this equation is probably right. But essentially what I'm saying is we're going from add to XOR, add to store, add to AND. What's the probability that add goes to XOR, add goes to store? What's the probability that add goes to AND at time equals 1? What's the probability XOR goes to AND from here to here? What's the probability XOR goes to load, XOR goes to BIC, right? What is that probability? And if you build a model with those probabilities, you can predict, you can use it to predict the next state, right? You can use it to determine, is this sequence coming from this model, right? So essentially, you can use this Markov model to enhance your classification. If your classification's weak, classification in itself is missing contextual information, what's coming before, what's after it, right? Markov model can be used to enhance the sequence of instructions, the sequence of words, okay? So what do we do here? In this case, we're using Markov model to answer, given the sequence of states, what's the probability it came from this model, okay? What's the probability? In this case, I plot hidden Markov model's output with respect to a sliding window size of 10. And I plot the probability of a particular 10 sequence coming from, what's the probability that the sequence comes or is related to the model that we generated, this Bij and Aij matrix, okay? We make it based on those two matrices. You have to do it ahead of time. Then you can say, well, if this is essentially the probability of a random string of instructions occurring, 1 over I to the n, and you essentially say, well, every time we get a 10 sequence of instructions, what's the probability that those 10 sequence of instruction came from this model, this Markov model that we generated before? And we can see here that the Markov model is picked up here, here, and here. So you can look at this, and this, and say, oh, we're probably in the add round key phase. A lot of this is done also for essentially anomaly detection in networks, right? You can do anomaly detection in networks using the same model. This model is used all over the place, right? This is not specific to a sequence of instructions in a microprocessor. I'm just using that example because that's what I'm doing. It's already here. You could use Google Translate. You could use any other model to talk about this as well. It's pretty much the same model, but different topic. And that's about it. I'm done. Any other questions before we go? I think I might have gone a little fast, but no one stopped me, so. Any other questions?
I don't got any.
Okay.
The Python
Yeah.
code?
Yeah.
Did you like have to get a library for that, or is that just built in?
Oh, so when you.
Oh, I didn't see the top part. Never mind.
Yeah, you're gonna have to next lab we're gonna actually do this, and you're gonna have to do a pip install. I'm actually writing up your next lab right now, your next assignment, and you'll have to pip install some of these libraries, but it makes it much easier because you can write this by hand, but you could just call the library and I think it's more valuable to understand how these classifiers work from a high level rather than trying to implement what's already been implemented. Right.
All right.
So
Looks cool.
yeah. All right. Any last questions before we go? That's going to be what your lab is basically next week.
Yeah, for the Markov model, like later in the slides, for the data collection of instructions, do you have something to automate that? Because I imagine it differs from device to device, right? Or,
Which one? This part?
yeah, for the.
I did this by hand.
So
I always automate everything. I'm pretty sure there's a way, but I couldn't figure out how to automate Atmel Studio to do that.
okay.
But a lot of the Python stuff can be automated. What I did automate was the data collection from the oscilloscope, though. Right? You can automate. You can call Visa to the scope and essentially pull data from the scope automatically without actually having to do anything, which is great. So it'll just sit there and collect traces for you instead of having to press the manual button like for hours, or the single capture button and save. Any other questions before we go? No? All right. Well, this is the last class with respect to lecture. Got to keep working on this stuff, but this is about it.
Okay.
I'll see you guys later.
Thanks, Kevin.
Yeah.
Bye.
Thanks. Bye-bye.